absolute value graphs practice. And so we're going to be emphasizing two things here. One, we're going to emphasize how, with at least some graphs, we have a few different lenses, a few different ways of looking at it. One is by viewing this expression as really just a bunch of transformations on the function y equals the absolute value of x, our standard graph. We're going to call that method A. However, we can also look at these graphs as just graphing a function on the inside of a set of absolute value symbols, and then taking the absolute value and just reflecting across the x-axis any parts of the graph that are below the x-axis. We're going to call that method B. And the method we're going to choose for deciding which method is appropriate is if the whole function is on the inside of our absolute values, we're going to use method B. If we can see that there are some transformations on the outside, we're going to use method A. And if there's something funky on the inside that we have to graph especially, and then other things, we might have to do a combination of both. All right. So that's the first thing. The second thing I would like to emphasize is that we know how to test our graph to see if it's right. So we can always test points. We can choose an x and then find the y, just using algebra. And by doing so, we should be able to test if a point is on the graph, and if it is, then our graph, we should be able to assess whether our graph is looking good or not. All right, so without further ado, let's see what we got here. So we got question 1. All right, so we have this function, y equals negative a half times the absolute value of x minus 4 plus 3. All right. And I can think of that as being somewhat similar to y equals a absolute value of b, x minus h plus k, if I want to. And then I can see how some of these numbers are somewhat similar to some of the our transformation letters that we used when we learned about transformations. Okay. So I can see that I have all these things on the outside of the absolute value, so it might not be that easy just to draw the function on the inside of the absolute value and then flip it. So I think it might be easier if I think about how does this affect the function y equals the absolute value of x. So to answer that question, I'm going to start by sketching the absolute value of x, the function that represents the absolute value of x. All right, so that is our standard graph. So it's like our vertical line graph, y equals x. However, when it was about to dip below the x-axis, it gets flipped up and points up like this. Another 45-degree line, but has a negative slope. And these two together make our function y equals the absolute value of x. And I've got a series of transformations here. I've got an a value of negative 1/2. So that means I've got some transformations here. I've got a compression, and that's vertical, by half. I'll use a different color here, so then I've got reflection over the x-axis. I hope it shows up on this video. I'm going to try and use green here for this other so we also have these translations. So we're shifting to the right 4, and we're going to shift up 3. All right. Now, so I'm going to go through these one at a time. First, we'll compress vertically by a factor of a half. All right, so I'm going to take each of my y values for each of my points. I'm going to divide it by 2. So I get 1 here. Half of 2 is 1. Half of 3 is 3/2 or 1.5. Half of 4 is 2. And I get a mirror image over here. Very nice. And I'm going to just try a dashed line here because I don't want things to get too messy. Although, probably this won't look very pretty by the end. And then I've got a reflection over the x-axis, so I'm going to take all these values and reflect them down here. All right, and then we're going to shift to the right 4. Oh, we use green for that. To the right 4, up 3. So this vertex goes up here. This point 1, 2, 3, 4, 1, 2, 3. This point 1, 2, 3, 4, 1, 2, 3. And I can see, and I'll put nice solid lines in here for this last one. All right. Oops. Could have used a ruler for that, really. All right. So I'm going to extend this a little bit. All right, and we were asked to, if you notice in the question, show the x and the y intercepts. So we've got an x-intercept here, and that is at the point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's the point 10, 0. And I've got another x-intercept here, and that's at the point -2, 0. And I've got a y-intercept here, and it's looking a little crowded, so I'm going to just do a little arrow in here. So that's at the point 0, 2. Okay. And that is our transformed function. Okay. So let's move on to question 2. So question 2, I do have 2 options. I could continue in this method. I could see this 2 as a horizontal compression by 1/2. And I could see this as a shift to the left, but I have to factor that 2 out of both of these terms. Okay, so I'm going to slow that down a bit. All right. There we go. Y equals the absolute value of 2x minus 1. Now, I think this is going to be easiest if I first, let's think about method B, which means I'll graph the inside function, and then we will reflect any negative values. Okay. And maybe I can talk about how we could solve it using method A afterwards. All right. So step 1 is I will graph y equals 2x minus 1. And so this is a line, and it has a slope equal to 2 over 1, which is the rise and the run. And it has a y-intercept of -1, equal to -1. All right, so I can sketch that. So I'll start with graphing y equals 2x minus 1. Oops. All right, so we'll start with the y-intercept of -1, and we'll sketch up 2 and over 1, up 2 over 1, up 2 over 1, and I might also sketch down 2 and over -1, or down 2 and over -1. Okay, great. And that's my original function. Now, step 2 is I'm going to reflect under the x-axis. So I'm going to take all these values, I'm going to reflect them up. So I'm going to flip these guys up, and that means instead of here, instead of being -1, -3, it become -1, +3. -2 and -5 becomes -2, +5. And there is our function. Now, I should probably list where the x and y intercepts are. So x-intercept is here, and it is at 1/2 and 0. And the y-intercept, ugly arrow, is at 0, 1. All right. Now, we didn't do this with the last question, but let's just talk about how we can test. All right, so can we test this graph? I should be able to pick any value of x and put it into this function, find out what the y should be, right? That's a table of values principle. I can just make a table of values, and I could plot the whole graph that way. So let's test a random value. Let's say 3. Let's see what happens when x becomes 3. So if x becomes 3, then I should get absolute value of 2 times 3 minus 1. And so I get the absolute value of 6 minus 1, which is 5. That's all equal to 5. So when x is 3, I should get a value of 5. Do I? And when x is 1, 2, 3, y is 1, 2, 3, 4, 5. Hey, great. Now, that wasn't the best point to test because that didn't really involve the absolute value at all. That would have been there anyway on the original line. So maybe I'll choose one of these values that reflects and just make sure they're on the right track as well. So maybe I'll try the value -2, or maybe -1. Let's try -1. So what about when x is -1? So when x is -1, I get 2 times -1, take away 1, which is going to be equal to the absolute value of -2 minus 1, which is the same thing as saying the absolute value of -3, which is 3. So I should get a value at -1, 3. And I do. Okay. So things are looking good. This graph stands up to some sort of table of values test. Okay. So let's move on to question 3. All right, so question 3 reads, well, it looks kind of similar to the last question here. So in that we've got a graph on the whole function on the inside of a set of absolute value functions. So we'll probably use method B, which means we'll graph the inside function, and then we'll call that step 1, and step 2 is we will reflect part of the graph. Okay, so part 1 is to say, okay, we're going to just graph, maybe I'll use another color here, the function y equals -1/4 x plus 1. All right, so this has a y-intercept, which is equal to +1, and it has a slope, which is equal to -1/4, which, I'll remind you, is either -1/4, or I could think of it as 1/4. And I can choose which my rise or my run is negative, as long as I don't choose them both to be negative, because a negative over a negative would actually make a positive value overall. All right. So I'm going to keep with red here. So the y-intercept was 1. And I'm going to rise -1 and run 4. Rise -1, run 1, 2, 3, 4. Or I could think of myself as rising +1 and running -4. 1, 2, 3, 4. Like so. All right. Now, part 2 is we're going to reflect. Oh, maybe we'll do that in blue. All right, so now we're going to take all these values and flip them up. And so it looks like something like that. All right, and I'm going to label my, x-intercept as 4, 0, and my y-intercept as 0, 1. All right, and maybe I'll do another test. So let's do a test. Let's choose a value, random value for x and y. So I'm going to let's try 0. Nice and easy, right? So if I plug 0 in for x, I should get y is equal to the absolute value of negative a quarter times 0. So it'd be 0 plus 1, which should be 1. So I should get a y value of 1. And I do. When x is 0, y is 1. And when x is negative 4, let's try that too. Y is equal to negative a quarter times 4. So 4 quarters is a whole, so it'd be negative 1 plus 1, and that's 0. Absolute value of 0 is 0. So I should, that's not good. Oh, oops, pardon me, we're putting in negative 4. So negative, negative, that's going to make it positive. That should be the absolute value of 2. Weird. And we get a value at negative 4 and positive 2. So we're looking good. All right. So that's the point, negative 4, 2, 0, 1. All right. Let's move on. Okay. So for question 4, again, we have this function on the inside of a set of absolute value graphs, symbols. So y equals the absolute value of x squared minus 4x minus 12. And again, we have the whole function inside a set of absolute values. So we're going to start with method B here. So we're going to graph on the inside. Okay, so step 1 is we'll graph y equals x squared minus 4x minus 12. All right. So let's see what we can do here. Well, this is going to be a parabola. And we have a few different ways of graphing parabolas. We can start with the roots. Well, we could use a quadratic formula as well to find the roots, which I guess is kind of like finding the roots. So maybe I should say factor to find roots. We could use a quadratic formula to find the roots. You can also, I'm going to just throw this one at you because you've seen this last year. We could do something called completing the square to rewrite this into some sort of vertex form is what we call it. All right, so I'm going to start by factoring. All right, so I'm going to start by saying, when I'm finding the roots, I'm finding where y is 0. I'm going to rewrite it like that. And then I'm going to say, well, maybe I can factor this. Things are looking pretty good there. It's pretty easy to factor. I can see it already. So two numbers that add to negative 4 but multiply to negative 12. Looks like x minus 6 and x plus 2. All right, and so that gives us roots. X is 6 and negative 2. All right, so that's pretty good. I could also have used the quadratic formula. So I could have said x equals negative 4, which is positive 4, plus or minus a square root of negative 4 squared, or 16, minus 4 times a, which is 1, times negative 12. And that's all divided by 2 times negative 1, or 2. We could find x is equal to 4 plus or minus a square root of 16 plus 48 over 2. 16 plus 48, I'm willing to bet that's 64, but it's been a long day, so I'm just going to bring the old calculator out. It's 64. Okay, cool. So we get x is equal to 4 plus or minus the square root of 64 over 2, which is to say x is equal to 4 plus 8 over 2, 4 plus 8 is 12 over 2 is 6. And 4 minus 8 is negative 4. Divided by 2 is negative 2. So, same roots. Okay. All right. So that gets us started. We can also complete the square. So that is to say, I can rewrite this in our form y equals a x minus h squared plus k. And then find the vertex of our parabola. You might not have thought about this in a while. We haven't reviewed it in class, but you did learn it in Pre-Calculus 11. So the nature of this vertex form of a parabola is to say that we have this thing, which is a perfect square, trinomial. And so I have to rewrite this so that I can have this perfect square trinomial I can factor. So I've got y equals x squared minus 4x minus 12. So what I'm going to do is I'm going to say I need a number to be added here so that it's going to be half of this number squared. So half of that is negative 2. Squared is 4. So I'm going to add 4 here. But I can't just add in 4, I also have to take away 4 so that it's equal to the line above. All right, and this is a perfect square trinomial. If I factor that, it gives me actually x minus 2 times x minus 2, and these grouped together give us negative 16. All right, and that gives us y is equal to x minus 2 squared minus 16. All right, so this is a different way for us to approach graphing a parabola. And we're going to see how these two different methods can be used to graph the same function. All right, so if I know the roots of our function, I don't think I've left enough room. Okay, I'm actually going to grab a new piece of paper so I can do a nice big graph, because I can see that actually we'll benefit from using a lot of extra space. All right. So we've got these roots at 6 and negative 2. And actually, I'm going to have a nice long y-axis. All right, so first I'll plot these points. 1, 2, 3, 4, 5, 6. And that's a point 6, 0, and negative 2, which is the point negative 2, 0. Now, that's fine. Now, I might recognize that this function is a positive, has a positive leading coefficient, which means it's going to end at positive infinity and look something like this. And maybe I want some specifics, so I might find the y-intercept. So I might also find the y-intercept. So let's find the y-intercept. And so that'll put in y is equal to 0 squared minus 4 times 0 minus 12, or y is equal to negative 12. So I've also got a y-intercept way down here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and that's the point negative, 0, negative 12. All right, and so we have to be able to connect those dots somehow, so you can see that we're going to have something going down like this, and the question might be, how deep should it go? If I want to know exactly how deep it will go, I can find the value directly in between the two roots, which is the point, I guess, 2, and I can plug in the value for 2 and find out what the y is. And when I do that, I get 2 squared, which is 4. minus 4 times 2, which is 8, minus 12. So I get 4 minus 8 minus 12. 4 minus 8 is negative 4. Take away 12 is negative 16. So I get the point 2 when x is 2, y is negative, all the way down here. 2, 4, 6, 8, 10, 12, 14, 16. And I have the point here at 2, negative 16. All right. Oh, well, what do you know? That number sounds familiar. If I look at this complete the square method we did earlier, we found that this function was a regular parabola moved to the right 2 and down 16 units. So it's a regular parabola moving down 2, over 2 and down 16. All right, and that might ring a bell for you. And parabolas go over 1 and up 1, over 2 and up 4. All right, and we see something like that. I'm just drawing dotted lines right now. Because we still have to do our step 2. Step 2 is we're going to reflect. Uh-oh. Man, no matter how big I made this, I still didn't leave enough space. Alright, so for the reflect step, which is going to be in blue, we're going to take all these values and flip them up. And I didn't leave enough space, like a silly person. Oops. So we're going to put these guys curve upward. Not very pretty. All right, I've still got these x-intercepts, and the y-intercept will be at 0 and positive 12. All right, and I could test that values, if those values if I want. I could say test what happens when x is 1. And I'm not going to use the same table of values because this was for my original f of x. And now I'll just do the absolute value of f of x table of values. Oops. So let's choose a value randomly. Let's say negative 1. And let's see what happens to this function as I put in negative 1 for x. So y is equal to the absolute value of negative 1 squared minus 4 times negative 1. Oops, I'm not writing anything on the screen. Minus 12. Close the bracket. Not a bracket, absolute value symbol. So again, y is equal to absolute value of 1 plus 4, take away 12. So again, y is, why is that? All right, that's equal to 5 minus 12, which should be negative 7. So y should be 7 when x is negative 1. That's just luck. Y is negative 1, x is 1, 2, 3, 4, 5, 6, 7. So it should be up here. So it looks like when I sketched this, I could have made it a little bit higher, so it's not perfect. But I can tell that I'm kind of sketching the right kind of idea. I could have made it a little bit more accurate, and if I look down here, I can see that actually probably should have been more down here. Okay, that makes sense. All right, cool. So let's move on to question 5. All right, so question 5 is interesting because it looks like we have a normal situation like we had in the last one, a method B situation where we have some function inside a set of absolute value symbols. But in addition, we've got this negative on the outside. So we're going to need a combination of method A and B. But we're going to start with method B. So we're going to start by graphing, graph y equals x squared minus 9. All right, so this will be a parabola. we can do a couple of things here. We could factor to find the roots. Or we could use a quadratic formula. We could also complete the square. I don't think I'm going to do that this time. You can do it on your own time if you prefer. But I would say it's not that useful this time. All right, so what do we got here? Factor to find the roots. Okay, so this is a difference, subtraction, between two perfect squares. So this is a difference of squares. And that means we've got y is equal to x plus 3, x minus 3. Now, however, maybe I used a quadratic formula and I said x is equal to the negative, b is 0 in this case, so negative 0, which is the same thing as positive 0, but I'll fix that, plus or minus our 0b minus 4 times 1 times negative 9. And it's all over 2 times 1. So x is equal to plus or minus the square root of 36 over 2, which is the same thing as plus or minus 6 over 2. So x equals 3 and negative 3. And that's the same thing I see here. Okay, so let's start by plotting our roots. I need a lot of space. I shouldn't make the same mistake I made last time. All right. Hope that's enough space. I think it will be. All right, so I've got a point here at 3, 0, and negative 3, 0. And, all right. I should probably find the y-intercept. So the y-intercept will be at when x is 0, negative 9. So it goes down 1, 2, 3, 4, 5, 6, 7. Lost track. 4, 8, 9. All right, so I see something that looks a little like this. And I might remember with the parabola, I go over 1 and up 1, over 2 and up 4, over 3, and up the square of 3, which is 9. Over 1 and up 1 squared, over 2 and up 2 squared, 2 squared, which is 4. No, 4. God. And over 3 and up 3 squared, which is 9. Do I have any white out here? I do. I think I'm going to white those out. That's a little misleading. Oh, so much white out. I only need the tiniest dab. Man, white out is gross. Gooey. All right. That wasn't on the right place either. What was I doing? All right. White it out. Never happened. All right, so we should have a point here. All right, so we got a little sketch up like this, and that looks fine. All right, now we need to, for part 2, we're going to reflect. And so that means all of these guys are going to be flipped upward. And so that means instead of being at 0, negative 9, it'll be at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Positive 9. Now I'm actually going to just keep this as a dotted line. And the reason for that is we haven't addressed the last step. So if we look back at the original question, we actually weren't asked to graph y equals the absolute value of x squared minus 9, but y equals the negative version of the absolute value of x squared minus 9. So that means we've got a reflection over the x-axis as well. So that means, what color haven't I used much? All right, so step 3 is we're going to reflect the entire graph over the x-axis. All right, so this guy flips all the way back down to here to 0, positive 9. And then we look something like this. And like that. Now, those x-intercepts stay the same, but the y-intercept we're going to list is at 0, negative 9. All right, that was pretty funky. So maybe I'll test the point just to make sure. Maybe I'll test the point x equals 1. And we'll make sure that we get a point that makes sense. Well, maybe we'll try 2. Let's say x equals 1 and x equals negative 2. Let's see what happens. So y is equal to y is equal to the negative version of 1 squared minus 9, which is negative absolute value of negative 8, which is equal to negative 8. There we go. Okay, so 1 should give us a value of negative 8. And if I look on my graph, I do have a point at 1 for x and negative 8 for y. And maybe I'll try negative 2 as well. So y equals a negative version of negative 2 squared minus 9, which is y is equal to the absolute value, negative absolute value of 4 minus 9. Y is equal to the negative version of the absolute value of negative 5, which is, say, y is equal to negative 5. So when x is negative 2, y should be negative 5. And I look, negative 2, negative 1, 2, 3, 4, 5. Hey, look at there. Negative 2, negative 5. All right. Now, I am concerned that that isn't going to scan very well, so I'm actually going to go over this in black just to make sure it scans really clearly. All right. And there's our function. Okay, making progress, almost there. So looks like we have one last question, which is question number 6. All right. Oh, I guess we didn't have to show the y-intercepts for the last ones. I think it's good standards and practices, but you don't really have to. All right. So looks like this is another method B situation where we have these absolute value symbols and everything on the inside. So we're going to graph y equals f of x first, and then step 2 is we'll reflect to make y equals the absolute value of fx. All right. Okay, so step 1, so we've got the function, we'll graph y equals x times x plus 2 times x minus 3 times x minus 4. All right, so I will start by finding the zeros, or the roots, which is at x is 0, x is negative 2, x is 3, and x is 4. So I'm going to plot those points. And negative 2, 0, 3, and 4. Now, maybe I feel pretty confident in plotting this out. And I know where it's going to end up. Maybe I don't. So let's see what happens if I don't. If I'm not sure where to go from here, I'm going to choose a random value for x. Let's say x is 1. So we'll try x equals 1. And we'll just make it a table of values. Why not? So when x is 1, let's test here. So we got y values, which are going to be y is equal to 1 times 1 plus 2, which is 3. 1 minus 3 is negative 2. And 1 minus 4 is negative 3. So I'm going to get y is equal to 1 times 3, which is 3, negative 6, positive 18. Okay. So when x is 1, y should be up here somewhere. And I'm just going to plot it up there. I'm not going to connect all those dots, obviously, but it helps me orient myself. 2, 4, 6, 8, 10, 12, 14, 16, 18. I actually got pretty close there. All right. Okay, so that tells me between these 2 points I probably dip upward. And I don't see any kisses. There's no duplicity. There's no powers of 2. There's no powers of 3. No repeated roots. That means I shouldn't see any kisses or any inflection points. All right. I know some other tricks here, but maybe I'll try one more just to be safe. All right, so let's just try when x is negative 1. So then I got y is equal to negative 1. Negative 1 plus 2 is 1. Negative 1 minus 3 is negative 4. And negative 1 minus 4 is negative 5. So that gives us negative 1 times 1, which is negative 1 times 20, which is negative 20. So we get a value way down here. All right, so this is starting to paint a pretty clear picture to me. So it looks like it's going to dip down, and then up, and then down, and then up. Obviously, this dipped way up higher, and this dipped way down lower, but I'm not really too concerned with that. And I'm not done, because now I need to reflect. So I should use a different color for this. So these guys have to flip up. And so they're going to move up like this. And maybe we'll do this to indicate these guys aren't on the graph anymore. And that is our new graph. And the x-intercepts are negative 2, 0, 0, 0, that's 3, 0, and that's 4, 0. All right, and there's our funky graph. All right, let me know if you guys have any problems with it.